All right. In that video, there's a lot to talk about. So let's go back to why things become magnets. So long ago, when Kevin said, no, Derek said, sorry, Derek. When Derek said that magnets were the result of charges, was he wrong? No. Magnets are the result of charges. But not in the same way that you think with positive and negative attractions, because electrons have spin and create little magnetic fields. Okay, so here I have an electron configuration. Now this is a shorthand configuration. If you are in chemistry, then it makes sense to you. If you're not in chemistry, that's all right. Chemistry is just physics anyway. And this is why. Okay, so calcium has 2 arrows in its 4s orbital. That means what it's filled is it has a 1s orbital, which is the orbital really close inside really close to the atom's nucleus. 2s is just outside the 1s. 2p is just outside the 2s. Then you get to 3s, 3p. Then you get to 4s, 3d, which is what we have here, and 4p. So this is just a small portion of the periodic table, and we picked out some specific metals. Okay? Because some people say metals are magnetic, but not all metals are magnetic. There's only 4 that really work, aren't there? They show them at the end of that video. It's cobalt, iron, gallium, and I can't remember the third one off the top of my head. I think nickel. All right. So this is why only some metals are magnetic. Okay? Calcium, copper, iron, all metals. Iron is the only magnetic one. The reason why is it has unpaired electrons. Okay? So these arrows represent electrons. The up arrow and the down arrow represent the 2 different spins for electrons. Okay? You can think about it this way. An up arrow means clockwise spinning. A down arrow means counterclockwise spinning. Alright? Since they have opposite directions in their spin, they produce magnetic fields that go in opposite directions, which will cancel each other out. So the magnetic fields created by these 2 electrons cancel out. Does that make sense? Yes. The magnetic fields created by all these electrons cancel out. That's why calcium and copper do not make good magnets. And you cannot pick them up with a magnet. That's why you can't take a magnet next to your glass of milk and pull out all the calcium in it. Okay? But you can take a magnet next to a dissolved bowl of frosted flakes or corn flakes and pull all the iron out.
Really?
Yeah. Try it on your own.
Like
okay.
crunch up frosted flakes.
Take frosted flakes, put it in a bowl of milk or a bowl of water, and just leave it there. Okay? Or put it in a glass of milk or a glass of water, just leave it there. Okay? If it's in glass, you'll start to see little pieces of metal at the bottom. And if you take a magnet, you can move those pieces of metal around. Okay? Because it's little collections of iron. And it's not a bad thing. You guys eat iron all the time. It's good for you.
Ew.
No, it's good. Okay? If you're in a position where like you've lost a lot of blood, they tell you to eat iron because it helps in blood production and that sort of thing. All right. So back to iron. The reason why iron is a magnet is because all of these electrons are spinning in the same direction, creating magnetic fields that all align with each other. So it has little small magnets, little magnetic moments. Does that make sense? Yes, Richard.
So copper isn't one even though it has an unpaired?
It has 1 unpaired electron. It's not enough. And this 1 unpaired electron is not in the outer shell. It's actually in the inside. Okay? Has to be in the outer shell. Okay? Which is also too why sometimes if you excite magnets, if you excite superconductors, they can exhibit magnetic properties. Because when you excite an element, the electrons move to different levels. Okay? Any questions?
Yes. So in the video they talk about half-filled shells.
Yep.
Is it
This is a half-filled shell.
Okay.
Okay? Because each box can hold 2. This one is a little bit more than half-filled. Okay, but it's close to half-filled. So what they were saying in the video is that in the middle of all the blocks, Sergio's done talking. Okay. On the periodic table, if you look for the middle of the regions, you only have that column of 2. Then you have that little column of like 14. Then you have that block of 10. In the middles of those blocks, that's where you have the half-filled shells.
Oh, okay.
Let me draw a picture real quick of the periodic table. So it looks like this. Right?
Yeah.
This one is 2 blocks wide. This one is 14 blocks wide. This one is 10 blocks wide. Right? So in these regions, which are in the middle, that's where you find the magnets. Okay? Because that's where you have the half-filled shells.
Okay.
Alright? Okay. Now, has anyone ever heard of quantum mechanics?
Yes.
Okay. The spin of the electrons is the result of the quantum mechanics. Yes, I had a fun class on that. It is more exciting than it looks, but the equations are long like the one they showed in the video. Okay? And we're not going to do it, Sergio, don't worry. And all those equations, all those little symbols in the video, most of them lead to other equations, which is a mess. All right. So here we have magnetic and non-magnetic materials. So I thought it was a pretty cool idea in the video where they showed all the different soldiers, right?
Yeah.
All different soldiers were pointing in different directions, weren't they? Okay. So when all the different soldiers are pointing in different directions, that's like a magnetic material that's not currently a magnet. Okay. The reason why it's not currently a magnet is because we have all. It goes back to these electrons. The electrons in this region are all pointing one direction. The electrons in this region are pointing a different direction. Different direction, different direction, different direction. And all those magnetic fields then cancel each other out. So there's no magnet. Okay, does that make sense?
Yeah.
Now if you have a non-magnetic material like copper, the electrons don't all line up. So you have a bunch of little magnetic moments all pointing in different directions and you can't align them unless you use a current. We'll talk about that later. Alright, so all these domains have magnetic fields pointing in different directions. Now there's a couple ways I can go from here to here, both of which involve a magnet. Okay. If I want to make a quick magnet, I just need to take this magnetic material and set it next to a very strong magnet. And then what will happen is all of these small magnetic fields will align with the bigger magnetic field. Just like how I take a strong magnet and I put a compass around it, right? What does the compass do?
Well, it aligns the magnetic.
It aligns with the magnetic field, right?
Yeah.
This compass aligns with the magnetic field exerted by this magnet, because this magnet is much stronger than the compass. Does that make sense?
Yes.
That's why I started with that today. Okay? So the compass will align with the magnetic field it experiences. Just like these domains of different magnetic fields will all align with the magnetic field they feel to create a magnet. Okay? Now that will magnetize a substance, but it won't be a lasting magnet. Eventually, the domains will go back the way they were. If I want to make a lasting magnet, and this is how magnets are made within the Earth's core, all right? I need to take this substance and I need to melt it. Okay? Because when it's melted, it's no longer a solid, it's now a liquid, and things flow a lot easier in liquids, don't they?
Yeah.
So these domains, instead of just reorienting the electrons, these domains can kind of reorient themselves. So if I melt a magnetic material, and I have it subject to a magnetic field, meaning it's melted and it's within a magnetic field, okay? Then all these domains are kind of free to move, okay? Then when I have it melted in the magnetic field, I stop heating it and I start to cool it. As I cool it, what happens to the liquid metal? Becomes a solid, right? You cool a liquid, it becomes a solid, just like ice. You freeze water, it becomes ice, right? If I take molten iron and I cool it, it becomes a solid again, right? But since all of these electrons are aligning their field as it cools, they all freeze or solidify in this orientation, which then creates a magnet that's very difficult to make not magnetic. Right? So it's what's called a rare earth magnet. It's made deep in the core of the Earth, where a metal has been molten, and then it freezes subject to a strong magnetic field. And then they all align, and you get a very strong magnet. Right? The horseshoe magnet we looked at yesterday, the little silver magnet we looked at yesterday, those are strong magnets. They are magnets that were formed by melting and being subject to a magnetic field, and then being frozen in that magnetic field. Right? Does this kind of make sense? Okay. So now you know why magnets work. And like Derek said earlier, it is a result of charge. But it's not positive and negative attraction, it's how the electrons are spinning. Because as the electrons spin, they create their own magnets. And they align within the magnetic field they feel. Any questions, Richard?
How does like a magnet is like one is stronger than the other if they're all the same orientation?
Magnets that are formed by the whole melting process, every single domain in that magnet is pointing in the same direction. Okay? If I magnetize material like this one, then my magnetic field that's magnetizing it might only be strong enough to magnetize just the domains on the surface. It might not magnetize all domains. Or it might take these domains and get them all pointing in kind of the same direction. Okay? So I might have all domains kind of pointing, like some domains over here pointing this way, some domains over here pointing this way, and some domains pointing that way. Okay? So they're all kind of pointing in the same direction, right?
Yeah.
So when I add up all their vectors, we get a vector pointing that way. But if all of these domains were all pointing straight up, then the vector addition will be a much greater vector, which makes a much stronger magnet. Does that make sense, Richard? Okay. Any other questions? Any other questions? Okay. The field of magnets is one of the ones that's studied the most currently in physics, right? Because of the whole idea of quantum mechanics and the alignment of magnetic fields. Right. Any other questions? Any other questions? Anybody?